All right, Prop 32 says, in any triangle, if one of the sides be produced, the exterior angle is equal to the two interior and opposite angles, and the three interior angles of the triangle are equal to two right angles. So we're kind of proving two truths at once, which really, like, given some of the propositions that we've found, the second truth really just falls out immediately from the first truth. So the first thing that we're going to prove is that the exterior angle is equal to the two interior and opposite angles. So in other words, if we have our triangle ABC and we produce one of the sides, say BC, we produce it to some point D, what we want to prove is that this outside angle, ACD, is equal to the sum of the two interior and opposite angles. So in other words, we want to prove that angle A plus angle B equals angle ACD. So that's the first thing that we will prove. So let's do that. All right, how do we do it? So, first things first is we're going to say, we're going to let CE be drawn through the point C parallel to AB. So I want to draw a line through C that is parallel to AB. Just to avoid this becoming an obscenely long video, I'll try to just kind of eyeball this. That looks pretty good. There we go. So here's our line CE. So I say, I'll say first construct CE parallel to AB. And we just got done doing that. That was 31, yeah. Prop 31 that allows us to make parallel lines now. All right, so we've made CE, and yeah, here's a good place maybe if you'd like the more interactive side of this rather than just seeing how Euclid did it. Based off of that, that's the first step. I don't know, maybe see if you can prove based off of this and maybe the last couple of propositions that we proved. See if you can figure out how to show that angle ACD equals angle A plus angle B. Right. Well, so what does Euclid say? If CE is parallel to AB, then let's see, how should I write this? I could just write the conclusion. What does Euclid say? He says, then since AB is parallel to CE and AC has fallen upon them, the alternate angles BAC, ACE are equal to one another. Yeah, I think I can just say that rather than, restating CE is parallel to AB and then AC essentially acts as a transversal line. And our last few propositions said something about that case of a transversal falling over parallels. So, but I'll just jump straight to the conclusion of it, which is that angle BAC is equal to angle ACE. And this is by Prop 29. So just taking a look at the diagram of what this says, angle BAC is this top angle up here. So we're saying that this is equal to ACE. Yeah, and that makes sense because you want to think of AB as being the parallel lines, and then AC is the one that is sort of cutting through it. So, yeah, BAC, this angle right here, is equal to this angle because AB and CE are parallel. So, and Prop 29 gives us that. We can kind of do this again, since AB is parallel to CE. But this time we're going to look at BD as being the transversal. So we're going to say AB is parallel to CE, and then there's this BD line that is cutting through them as a transversal. And because of that, we get that angle ECD is equal to angle ABC. And that's the exact same proposition. Prop 29 gives us that. So ECD is this guy right here, is equal to ABC. Yeah, and once again, because if you imagine AB is parallel to CE, and then we draw this line cutting through, then these interior, how does he say that exterior angle is equal to the interior and opposite angle. I guess he doesn't quote the way that it's it's quoted in Prop 29, but that's where it's coming from, is that this angle right here, angle B, is equal to angle ECD because of the parallel lines. Right. Well, okie dokie. What does he say? But the angle ACE was also proved equal to the angle BAC. So therefore, the whole angle ACD is equal to the two interior and opposite angles BAC, ABC. So just to kind of maybe write out a few more details of that, we have, maybe I'll say, everybody's favorite math word, thus. Angle ACD is equal to angle ACE plus angle ECD, and this is kind of messy. It's not my favorite. I don't like doing sort of equality through two lines like that, but it reads well. So, but we also just said angle ACE is equal to angle BAC, and angle ECD is angle ABC, which is what we wanted to prove. That was the entire idea of this first statement. The exterior angle is equal to the two interior and opposite angles. Yeah, that's what we just said, or what we just proved, is that ACD, this exterior angle, is equal to BAC plus ABC. So the first part is done. We've proved the first part of this. Right. And then from this actually is where we get the very last piece of this, because to both sides of this, so this, from this angle ACD equals angle BAC plus ABC, we're going to add into that angle BCA, or ACB, I guess is how he wrote it. So we get that angle ACD plus angle ACB is equal to angle ACE plus angle ECD plus angle ACB. All right, we just took this same equality and we just added ACB to both sides of it. But look at what we just did in the in terms of the diagram. So on the left-hand side, ACD plus ACB is equal to ACE plus ECD plus ACB. Oops, this was not what I wanted to write. I was like, okay, shoot, sorry. Yeah, I bet that was really confusing. I didn't mean to write those ones. I meant to write what they're equal to, because angle ACE is equal to angle BAC. Whoops, this is what I should have been looking at. Angle BAC. Sorry, I know that's confusing, and now I'm having to write over my own writing. Yeesh, it's ugly. Sorry. Yeah, ACD plus ACB is equal to, this is what I wanted, BAC plus ABC plus ACB. So the internal, this right-hand side is the internal sum of the angles, or the sum of the internal angles, interior angles. I can't talk today. Right. But we have a proposition that says something about this left-hand side, ACD plus ACB. But, so I'll say but, angle ACD plus angle ACB equals 2 right angles. And that comes from Prop 13, which basically is the one that says that a straight line is 2 right angles. So just to kind of finish it off, angle BAC plus angle ABC plus angle ACB equals 2 right angles. And that's what we needed to prove. So kind of cool, because this is generally just kind of given to most of us. Like whenever you're learning geometry, usually, you know, you're just kind of told, like, hey, yeah, and you know, the internal sum of the angles is 180 degrees, and maybe it never really gets rigorously proven. So here's where Euclid rigorously proved that fundamental fact about triangles. Yep, that's it. QED, therefore, etc.